Hello student, welcome to the session 7 of this paper, Electricity and Magnetism. So in this chapter, we are going to study about the self-inductance, its definition, explanation and expression for the energy stored in the inductor, and also we are going to study about the magnetic field. What are the learning objectives of this session is that we have to understand the concept of self-inductance and to derive the expression for energy stored in the inductor. Session outcomes. After the end of this session, we should be able to tell what is the self-inductance, its definition, its coefficient, and what is the SI unit of this self-inductance, and also enable to derive the expression for the energy stored in an inductor. Before going to the lesson, we should know what are these things. What is magnetic field? What is magnetic flux? And what is the induced EMF? So this magnetic flux is something which is distributed around a bar magnet or any magnetic material. So this distributed thing can be sensed by bringing another magnetic material or another bar magnet near to this magnet, and at that time we will come to know that these two magnets will be either repelled or attracted. So this happens because of the something that is called as the magnetic field, and this magnetic field is characterized by the spatial lines. They are called as the magnetic flux lines. These magnetic flux lines are also distributed wherever the magnetic field is there. And these magnetic lines of force or flux lines indicates the direction of the magnetic field at a given point. And what is the induced EMF? So induced EMF means it is electromotive force. This electromotive force is sometimes induced into an coil whenever the magnetic flux linked with that coil is changes. So it is the consequence of the Faraday's law that we are going to study later. So now I am coming to the Faraday's law. According to this Faraday's law, whenever a conductor is placed in a varying magnetic field, an EMF is induced in the circuit. And if the conductor is closed circuit, then the induced current flows through it. So I will explain this more clearly with the help of a diagram. So the second point is that the magnetic field, the magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux linked with the circuit. And these things we'll see with the help of this diagram. So you look at this diagram. Here a coil is there. This coil is connected to an ammeter. Simply there is no battery. Be sure that there is no battery is connected to this circuit. Simply it is a coil connected to an ammeter. Don't have the battery. But here we have the magnetic bar magnet is there. So around this bar magnet, magnetic field is there, that is linked. The flux lines of this bar magnets are linked with this coil. So we are changing the flux amount of flux linked with this coil. How it can be done? Just you can move either towards the coil or away from the coil this bar magnet. This bar magnet is suddenly moved either towards the coil or away from the coil. So by doing this, so you are changing the flux linked with this coil, that leads to induction of some electromotive force in this coil, and that induced EMF in this coil generates some current through this circuit, and that is indicated by this ammeter. So this thing is discovered by the Faraday, and it is called as the Faraday's law. So therefore the amount of current induced or the amount of EMF induced in the circuit depends upon the flux, the rate of change of flux linked with this coil. This rate of change of flux changing, its changing rate depends upon how fast you are moving this bar magnet either towards the coil or away from the coil. So that decides the rate. So this is the Faraday's law. So therefore, whenever a conductor is placed in a varying magnetic field, here we are placed in a coil and EMF is induced in the circuit. Next, as I told, the magnitude of the induced EMF is directly proportional to the rate of change of flux linked with the circuit. So this rate of change of flux depends upon how fast you are moving the bar magnet either towards the coil or away from the coil. So this Lenz's law tells that the direction of an induced current is always such as to oppose the change in the flux or the magnetic field produced by it. So what happens once the flux changes, the EMF is induced in the coil, and that induced EMF generates some current. The direction of that generated current will be in such a way that it opposes the change in the flux of the magnetic field. So that is given by this Lenz's law. Next, so here same experiment is there. So current increasing, actually arrow mark should be on towards the right side, it is left side, but here it is written that current increasing means you are moving the bar magnet suddenly towards a coil. So the flux is increasing in the coil, so that leads to induction of more EMF in the coil, and that leads to increase in the current. So here current decreasing means flux associated with this coil is decreasing. So that means you are moving the bar magnet away from the coil. So that leads to decrease of the current. So these things are explained in this diagram. It is the same diagram. It is used for this phenomena. And whenever the magnetic flux, again same thing is written here. Whenever the magnetic flux linked with the coil changes, an EMF is induced in the same coil and is known as the self-inductance. And this is called as the self-inductance. It is the property of a circuit which causes it to oppose the change in the current flowing through it. So this induced self-inductance next opposes the flow of current through it. It is also called as the electromagnetic inertia of the circuit or coil, because this induction of EMF takes place only when the flux changes place. Hence, because of that reason, this inertia, the term inertia, comes here. So, after knowing the self-inductance, we'll have some equations here. So this whenever current flows in a circuit, magnetic flux linked with the coil changes, and it is directly proportional to the magnitude of the current. Actually, the flux linked with the circuit increases the current. So therefore, flux and this current are proportional to each other. And you remove this proportionality sign, you will get a constant generally, and this is called this proportionality constant is denoted here as a L, capital L, and here L is called as the coefficient of self-inductance of the coil, or simply the self-inductance. So definition: self-inductance of a coil is defined as the magnetic flux linked with the circuit uh, when unit current flows through it. So you can write this equation as L is equal to 5 by I, 5 by I. So I, when I goes 1, L becomes 5. That means flux. Self inductance is equal to the flux lines when the current becomes 1 ampere or unity. So, from Faraday's laws of electromagnetic induction, as I explained, the induced EMF is E is given by E is equal to minus d phi by dt. D phi by dt is the rate of change of flux, and that is equal to the induced EMF. And here negative sign comes because this induced EMF sends a current which is opposite to the the external current, or which opposes the change in the flux. So substitute phi is equal to Li in equation 2. This is equation 2. Then it becomes E equals minus L into di by dt. You are substituting phi is equal to Li here. So it becomes L into di by dt. L is a constant, so it is taken behind this differential operator d by dt. When di by dt is 1, then E becomes equal to L. So hence coefficient of self-inductance is equal to the induced EMF in the circuit when the rate of change of current through it is a unity. In this way also you can define the self-inductance. The SI unit of self-inductance is a Henry. So using this conduction, suppose when di by dt is equal to 1 ampere per second, then we can define here 1 Henry. 1 Henry means when a voltage, when if 1 volt is induced in the coil, when the rate of change of current is 1 ampere per second, then inductance is 1 Henry. So in this way, self inductance is defined. Next, we'll go for another point called as the energy stored in an inductor. So for that, just I will go through this. So this is another example for induction of flux in the coil. So as soon as the battery is started on, the current starts flowing this coil, and the magnetic field builds up in the coil. So that is shown in this diagram. So next, uh, we are going to derive an expression for energy stored in an inductor. So in this diagram, you are looking at a simple circuit diagram where a battery is there, and this battery and your key is there. It is connected to a resistor and an inductor. All are in series. So here what happens, when the key is inserted, the current starts flowing through the circuit, and the magnetic field in the coil starts building up. So as the magnetic field in the coil starts building up, energy starts storing in the inductor. And here, what is the function of this resistor? This resistor simply consume the power given by the battery in the form of energy, or the energy is dissipated as a thermal energy in this resistor. So these two things happens when the key is inserted. So the power consumed here is partially taken by this resistor and partially taken by this inductor, and the energy consumed by the resistor is simply dissipated in the form of heat energy, but the energy consumed by the inductor is stored in it as a magnetic energy. So for that, we will have this expression. So if I be the current in the circuit at a time t, then by KVL. So actually here, what happens? This buildup of energy continues until the current becomes maximum in the circuit. Because once the key is inserted here, the current in the circuit starts growing. Once the maximum amount of magnetic field energy is deposited in the inductor, it no more store the energy further. So at that time, what happens? The given the power given by this battery is simply consumed by the this resistor in the form of heat energy. So therefore, the time t here means it is the time at which the current becomes a maximum, or the time at which the maximum energy is stored by the inductor. So by KVL, Kirchhoff's voltage law, we can apply KVL to the circuit. So according to that, it becomes E minus L into di by dt is equal to IR. So this L into di by dt, as you know, it is voltage drop across the inductor. And simplify this equation, L into dt is equal to minus L dt is equal to IR dt. Dt is taken on both sides. Then you rearrange the terms like this, and here this edt is the work done in the battery in the time dt, because the work is done by the battery in supplying the power, electrical power, to these two things. So that is written in this way. To get the whole work done in the time 0 to t, during which the current goes from 0 to I, we have to integrate the equation 1 and also multiplying 1 by I current. Therefore, what happens to this equation 1? You see, multiply equation 1 by I current, then integrate. So it becomes 0 to t ei dt is equal to 0 to t I square r dt plus 0 to t L into di. For this last term, integral limits are 0 to I, because it is a current which goes maximum in the inductor. So same thing, you write as it is, but you integrate this second term in the RHS side, it becomes L into I square by 2, just by integration. Because L is a constant, so you are integrating I with respect to uh, di. So therefore, it becomes L into di square by 2. So this 0 to t ei dt is the total power given by the battery to the circuit, and this total power given to the circuit by the battery is consumed by these two things. This term 1 indicates the energy consumed by the resistor in the form of heat energy, but the second term Li square by 2 indicates the energy stored in the inductor. So this energy will be stored in the inductor in the form of the potential energy, and that is represented as a U. So therefore this U is equal to 1 by 2 L I square. So we got an expression for the energy stored in the inductor. So we'll move back to the same thing. Same thing is derived here also. And suppose if I becomes equal to 1 ampere, then W becomes is equal to 1 by 2L, or L is equal to 2 watt. So using this condition, we can also define this coefficient of self-inductance as is numerically equal to twice the work done in establishing magnetic induction accompanying unit current in this circuit. Then energy density of the magnetic field is given by energy density is equal to 1 by 2 B square divided by mu naught. We are not going to derive here, just expression is given. Energy density means energy per unit area covering the coil. So that is R in any region where magnetic field is there. So that is equal to 1 by 2 B square divided by mu naught, where B is the magnetic field intensity, and this mu naught is the permittivity of that area. So at the end of this session, you understood what is the Faraday's law, and you also learned the Lenz's law. And definition and units of self-inductance are also studied, and the expression for energy stored in an inductor is also derived. And here we'll see some MCQs. Inductor tends to block dash current but pass dash current. So inductor tends to block AC current and but passes DC current. Why it blocks AC current? Because AC current continuously changes its direction, so that leads to neutralization of energy stored in the inductor. So that is why it blocks. Next, an inductor acts as a dash for a dash current through it. So inductor acts as a simply resistor for a direct current, means DC current when it is flowing through it. Self-inductance is termed as electrical inertia. As I told, the self-inductance comes only when the flux is changing. So it is a type of inertia, like inertia of a body. Inertia of a body means the body cannot change its position itself unless until some force is exerted on it. In that way, it is also a type of inertia, because self inductance cannot be there in a coil unless there is some change in the flux. So that is the weakness of the inductor. Next MCQ. Energy stored in a magnetic field is directly proportional to 1, the point 1, the magnitude of the magnetic flux, point 2, the magnetic flux density, point 3, the number of turns, and point 4, the rate of change of magnetic flux. As I explained just now, uh, it depends upon points 3 and 4. That means the number of turns in the coils are important, and the rate of change of magnetic flux is important, and hence the answer third and fourth. And the induced EMF in a closed coil of wire, according to Faraday's law, is proportional to 1, the magnitude of the magnetic flux, the magnetic flux density, the number of turns, the rate of change of magnetic flux. Here also the options are third and fourth. The number of turns and rate of change of magnetic flux are very, very important. So summary, you have studied all these things, and these are the reference books you can go through. Thank you.